Ladies and gentlemen, my name is Tetsuo Takayama from Yamagata University. Thank you very much for choosing me for the Best Research Award of International Research Awards on Composite Materials. The title of this paper is Proposal and Verification of the Thermoplastic Surface Shear Strength Evaluative Method. Introduction of this paper. Thermoplastics were used in a wide range of applications in transportation, electronics, medical care, and daily necessities because of their lightweight and excellent mass productivity. Two industrial properties required for plastic products. First one is bulk properties. Second one is surface properties. Bulk properties include impact resistance, rigidity, strength, fatigue property, and so on. Surface properties include scratch resistance, abrasion resistance, and friction properties, and so on. In this study, we focused on the scratch resistance. Factors governing scratch resistance include indentation hardness and surface strength, and so on. For indentation hardness, we have studied viscous hardness and found that Taylor's rule is valid. Scratches are made by pushing and sliding the indenter, pushing and sliding. So shear load is generated in addition to the pushing load. A method to evaluate the resistance characteristics of this shear load have not been proposed until now. So, purposes of this study are: first one is a method to evaluate the resistance characteristics to shear load is proposed and its validity is evaluated. Second one is using the evaluated resistance characteristics, a model is constructed to explain the frictional force obtained in the boron disk test. Next slide shows materials used in this study. Details of the thermoplastic pellet used for this study are shown in this figure. Polypropylene PP, thermoplastic polyolefin TPO, and polystyrene PS were used as general-purpose plastics. Furthermore, polyoxymethylene POM and polyacrylonitrile styrene copolymer ABS were used as engineering plastic and polymer alloys, Particularly for polypropylene PP, two types are targeted. First one is block type. Second one is homo type. With the homo type, here's are prepared to subtypes. First one is normal type, which called homo PP. Second one is high modulus type, which called HMPP. For TPO, two types were prepared. First one is low modulus type, which called LMTPO. A second one is a high modulus type, which called HMTPO. After the pellet were filling into the microelectrode injection molding machine, injection molding was used to obtain molded products. The molded product shapes and dimensions are presented in figures. Molded products of two types were prepared for this study. First one is beam-shaped. Second one is disc-shaped molded products. As described herein, the yield shear strength of the molded product surface is designated as the surface shear strength, tau s. The overlapped short beam shear test is proposed as a method to evaluate this strength. Left figure shows a schematic diagram of the overlapped short beam shear test. For this method, specimens of the same type are overlapped and subjected to a 3-point bending test with a shorter span. The overlapping surface becomes the neutral plane of the entire specimen, resulting in zero bending stress and only shear stress. This principle and the fact that stiffness decreases considerably as the materials are used to find the stress required for the surface of the molded product to begin yielding shear. The tests were conducted using a tabletop tensile and compression testing machine with a span of 10 mm and loading speed of 10 mm per minute. The shear stress was obtained from the obtained load deflection curve using this equation. Stiffness was obtained by differentiating the curves by deflection to obtain a shear stress stiffness curve. This one. Right figure presents an example of a shear stress stiffness curve. For all the materials tested in this study, the curves were similar to this figure. As the load is applied, stiffness increases. It then drops sharply in the middle of the curve. Then, as the load is increased, the stiffness becomes higher than before. It reaches the maximum value. At this maximum value, the surface shear of the mold product is regarded as beginning. The shear stress at this point is defined as the surface shear strength. In this case, the surface shear strength is this point. A boron disc test using a disc-shaped molded product made by injection molding is performed using a slide friction tester to evaluate the time dependence of the frictional force. Left figure shows a schematic diagram of the boron disc test. Stainless steel indenter had a 4.0 mm radius, 4.0. Right figure portrays a graph showing the change friction force obtained from the boron disc test along the time axis. As the figure shows, the friction force increased rapidly at the beginning of the test. Subsequently, it converges to a constant value. This convergence value of friction force, which is defined for this study as the friction force obtained by boron disc, was used as a characteristics value for constructing the model. This figure shows the relation between surface shear strength and yield stress. As this figure shows, a proportional relation exists between surface shear strength tau s and yield stress. Irrespective of the materials as expressed in equation, this one. Considering the stress state under which this relation holds in the Formises yield condition, the stress produced in the overlapped short beam shear test was regarded as a triaxial shear stress, which indicates that the tests conducted for this study were evaluated in accordance with expected principle. These results indicate that only shear stress is appreciable to the surface of the molded product by performing the overlapped short beam shear test. The shear stress found using the boron disk test is always assumed to reach the surface shear strength, which might be explained using a mechanical model that explains the frictional force constructed based on the adhesion theory. In other words, for this study, frictional force M generated during the boron disk test is explained by left equation, this one. In that equation, AS denotes the indenter contact area. Assuming that the contact area, the shape is spherical deficient, right equation is obtained. Therein, R represents the indenter radius, and delta denotes the indentation depth, which is divided into an elastic deformation component and plastic deformation component. Left figure shows a graphical comparison with the calculated and measured friction force. For most of the materials, the value calculated using this model were found to explain the friction force obtained from the boron disk test. However, only LMTPO were calculated value found to be lower than experimental values, because LMTPO was the softest material used for this study, and therefore indentation depth was greater than for the other materials. It's possible that deformation attributable to loading might have reached bulk region. For confirmation, a 1 Newton boron disk test with TPO was performed. The result is shown here. These results indicate that the friction force obtained from the boron disk test of thermoplastic injection molded part is explainable by surface shear strength and by the contact area of the indenter, which indicates that the surface shear strength can be ascertained based on the overlapped short beam shear test we have proposed. In summary, we propose the overlapped short beam shear test to evaluate the surface shear strength of injection molded thermoplastics. Surface shear strength is proportional to yield stress. Finally, surface shear strength is related to the frictional force obtained from the boron disk test, thereby validating the proposed method. That's all my presentation. Thank you for kind attention.